Okay, good morning. Last time we discussed the continuous time signals. Continuous signals. Any questions? Everybody reviewed, right? And you can start the homework. Any questions?
The homework is on the Wicca?
Huh?
The homework is on the Wicca website?
Yes.
Okay. And what do we get the log information from?
The log information is, a website, right? The password is signal.
Actually, I already got that.
Signal.
Okay.
Okay.
Thank you.
Questions about the textbook, the lecture notes, anything? Everything is good? Okay. Today we are going to discuss continuous systems. Sometimes we need to discuss quantities that deal with time, or deal with temperature, or some position, like in physics, the position, temperature, time. All these are variables, and if we want to describe this kind of systems, usually we need to use a continuous system. Some others looks like not continuous, but we still need to use a continuous system concept. This is the first type. Second, for example, the electric charge. Electric charge in the circuit. We can count 1, 2, 3, right? But usually the number of charges are very large, so we cannot do that. So we are going to use like a continuous. The electric charge is a continuous variable. So charge in circuit, and molecules. Molecules in chemistry. Molecules also we can count molecules 1, 2, 3. But again, the number is very large, so we cannot use a discrete system. We need to use a continuous. Some other system, for example, dealing with people. How many people? Also we can count, but also we can use a continuous system. So all these ones are typical continuous systems. In this class, we only deal with a system as a function of time. Function of time. So mathematically, just ft. Usually in math we say fx. This x can be t, can be people, can be anything. So we just use t to represent this one-dimensional variable. So we only deal with t. So usually we say the input is xt, and the system of the output will be a yt. This is better, not just the function f. But that's the same thing, right? ft, xt, yt, they're the same, just the functions. And also, we are going to use the differential equations to describe this kind of continuous systems. Time domain models of a system. The first one is the first order system. We are in electrical engineering technology, so we deal with the circuit. So anyone still remember what is the first order electric circuit? What kind of circuit is called the first order electric circuit? What kind of device we should have? For example, if we have this is the source, right? We need to have a source, and we have a load here. This is a resistor. Is this a first order circuit? First order circuit, we need to have a energy storing element. What kind of element can store energy? capacitor or inductor, right? So for first order circuit, we can only have one of these two types. Right? We can have a capacitor. So we know this is called a RC circuit, right? We know this, right? The RC circuit. Or we can have a IL circuit. So we can have another one. So for example, an inductor. But we cannot have both. If we have both, that is the second order system. Right? So either we can have this one here, this is the straight, or we can have this one here. We cannot have both. So we use this one to represent. So this is the RC circuit, or LR circuit. So we have these two types. Okay, now we discuss an example. So here we have this source, that's a DC source, and we have this switch. At t equal to 0, we open this switch, and this one is a capacitor, and this one is a resistor. And this is C, this is R. So before t equal to 0, this switch is closed. So this is closed. That means this V0 will charge this C. So we can see the voltage on the C will be equal to the voltage source. And at t equal to 0, we open this switch, then the capacitor will discharge through the resistor. What we want to know is, we want to know the voltage here, VO, output voltage, because this is a parallel circuit. So the voltage on the capacitor equals the voltage on the resistor. So anyway, we want to know this one. So how to analyze this system? This is a very simple RC, parallel RC circuit, first order. So we are going to use because we are interested in when t greater than 0. When t is greater than 0, this one is open, so this one has no effect at all. So the circuit just looks like this. We only have this part here. We are going to use Kirchhoff's current law. That means this current plus this current equal to the total current, which is you consider this one is gone. So this current plus this current equal to 0, right? So that is the Kirchhoff current law applied to this node. The sum of the current equals the total current, which equals 0. Right? So the current on here is so IC plus IR equal to 0. That is from KCL. And what is the current on the capacitor? That is C dV dt. Then plus what is the current on the resistor? The resistor, we know the voltage here is V0. So we just V divided by, we can write V0, we just write V, okay? And V divided by R. That is Ohm's law. So C dV dt is the voltage, is the current flowing through the capacitor, and V over R is the current flowing through the resistor. And these two currents add up together equal to 0. Right? So that from Kirchhoff's law we get this equation. Right? So how to solve this one? We move this one to the right hand to here. So dV dt will plus divided by C. So CR or V equal to 0. We divided by C on both sides. We get this one. And then we move this one to the right hand side. So this one will be equals negative or negative. Equals negative this. Then I move this one to here, so switch this position. So this one here will be V, this one will be dt. So I get this from here. Now how to solve this one? We just take the differentiation integration on both sides. So this will be equal to this. dV and this. We know log 1 over V integration, that is log V. And the right hand side will be equals CR, 1 over CR. So that's RC T. Right? And negative. And we need to determine the starting point and so this one here will be from 0 to T. And this one will be equals from 0 also to T. So this V at 0, that is the initial. When T equals 0, we have initial condition. So that's V0 here. And when T equals T, the time we are interested in, okay, so that V, just VT here. Okay? This one is in Math 168, right? Alright, so now this one will be, we just solve this here. So what we have is Vt equals V0 e to the power of T over Rc. We solve this very simple differential equation, we get this one. So, do you recognize this? Yes, right? So if I give you this circuit, what is voltage on the capacitor or in resistor? That is V0, which is the initial condition, then times e to the power of t, negative t over, we said tau, time constant, right? So in general, we said this one equals V0 e to the negative t over tau. What is this tau? This tau is called time constant. This is the time constant. For RC circuit, this is called RC. For LR circuit, anyone still remember this? Okay, that is R over L. L over R? Which one? R over L, right? L over R. So for LR circuit, is this true? Anyone remember that? I forget, okay, L over R or R over L. Okay. Alright, so from 111, we know how to solve this kind of circuit. So you may wonder why we get this result. Okay, this result actually is the solution for this differential equation. Right? So now you can see, when we analyze a continuous system, first one we write out the differential equation, then we solve it, that's all. Any questions on this? This is familiar, right? Okay, good. So the procedure to analyze a continuous system is first one based on laws, right? Circuit law, physics, no matter what, mechanics, control systems. We write out the equation, usually it's differential equation, relating the input and the output. Then we just solve the differential equation. And for the first order circuit is very, very simple. And we just take the integral, and we know this in Math 169. So on both sides, then we get the solution. Right? You read everything? Okay, next one we discuss the second order circuit. What is second order circuit? We have two energy storing elements at the same time. Two capacitors doesn't count. Two capacitors means the one, right? We can combine these two capacitors. Two inductors right? Do not work. Inductors can be considered as one combined. So that means we need to have a capacitor, we need to have an inductor. So one example is like this, and this is the switch, and we have R here, we have like this, right? This is the R, this is the L, this is the C, and this one is VS. At t equal to 0, we close this switch. Before t equal to 0, everything here, for example, is nothing. Right? The initial conditions all are equal to 0. So there's no charge on the C, there's no current flowing through the inductor, so everything is 0. But when t equal to 0, we close this switch. Right? So what we want is we want to find this again, this voltage here, Vc. So just this V as a function of time. And this one here is the current. But we are looking for the voltage on the capacitor. So how to analyze this circuit? This is a series circuit. So we need to use what law? The voltage law, right? So Kirchhoff's voltage law says the sum of the voltage, all the voltages must be equal to 0. And the sum of all the voltages along a closed loop must be equal to 0. So that means this voltage plus this voltage plus this voltage plus this voltage equal to 0. Or we can see this voltage plus this voltage plus this voltage will be equal to this voltage. Right? So that gives us the formula. All right, so we know the current here equals I, the voltage here equals C. So we are going to write the KVL for the voltage on the resistor. That one will be okay. We write first V R plus VL plus VC equals to 0, right? That is KVL. VR, that equals I times R. And VL equals L di dt. And VC, okay, VC just V. That one equals to 0. So we can see this write this as a function of time, Vt. Now we have okay. Look at this first order, but we have I and V, both unknowns. So we don't like that. We want to have only one unknown. So the other relationship is what is this I? Through this V. So I equals C dV dt. Right? This is the current passing through the capacitor. So I equals CV dt. From this two, I plug I equals this one here, so this RC dV dt, then plus here L di dt. So di dt, that will be LC dV squared dt squared, then plus V equals 0. Oh, now we can see this is the second order differential equation. We do not, because some of you are from CET, we do not need the differential equations. So I won't let you to solve this differential equation. The purpose for this here is to show that any continuous system can be represented by a differential equation. Right? If you are from EET, you need to take math 285, so you need to know how to solve this one. So anyway, the response is the solution for the differential equation. We solve this, and the solution can be written in two parts. Right? One is the transient solution. The next one is the steady state solution. This part, you should already know this. This one, it may be in AC or in DC AC circuit or in the 311 or 312. I'm not quite sure which one. Second order circuit. This is transient, means the solution will go to zero after some long time. So transient, gone. And this steady state means that will stay here for a long time when t equals infinity. Are you familiar with this? Anyone? In this example, for example, what is the steady state response? That means when t goes to infinity, what is this voltage? Look at here, this circuit. When t goes to infinity, at t equals 0, we close this switch, right? Okay, when t goes to infinity, very, very long time, what is this voltage? We can close. This one is already closed. What is the voltage on here? This is the DC source, DC voltage. After some long time, this one is short, right? The inductor will be short, so straight line. This one will be open, right? So open means there's no current in this loop. No current means no voltage drop across this resistor. And there's no voltage drop here. Right? So this voltage equal to 0 plus this V. So that means this V will be equal to Vf. So this part will be equal to Vf. So that means when t goes to infinity, this one will be just equal to Vf. And for this part, we need to solve this equation, but usually based on the values of R, L, R, and C. L, R, and C, based on the relative value of these three parameters, we are going to have different forms. And this one is in circuit. Later time when you study 477 for EET, or 478, 477 for EET, you need to study the systems, control systems. For example, when you pop up your trunk, the car trunk, the trunk will just open, right? And you want your trunk to open as fast as possible. But if you open too fast, it will vibrate. You open this, it will like this. If you want to avoid this vibration, you want to open this one, you pop it, it will just very slow. It won't vibrate. But you do not want this one too slow. So you want to be as fast as possible without any vibration. Does this make sense? So when you pop your trunk, if you're very fast, it will like this. Then you don't like that. Very slow, you don't like this too. You want fast, okay, then stop. We have three situations based on the parameters, the string, and also the force or something, the friction. For circuit, exactly the same, because both mechanical system and this circuit can be represented by second order differential equation. And they are determined, so what kind of solution you have, very slow or very fast with vibration, or just the perfect, based on all these three parameters. And so we can choose, when you design circuit, you can choose these three values then to design the perfect circuit you want. You may want a vibration, this oscillator. You may want to just reduce to zero slowly, discharge slowly. So that is another situation. So anyway, this solution depends on the relative value of this one. And the form can be, as we mentioned. So the first one is called overdamped. The solution is V transient will be equals to A1 e to the lambda 1 t plus A2 e to the lambda 2 t. Usually this one here will be smaller than 0. This one also smaller than 0 in a real circuit usually. So you can see this one is exponentially decreasing. This one also exponentially decreasing. So the result will be just like this. Like this one. So reduced to 0. No oscillating. So this is the first case. Right? The second case is critically damped. This one may be very slow. So maybe like this, or we can draw like this. So maybe very slow, like this. Like this. Not straight line, still exponential. And critically means that's the best case we want. So it will goes down, but very quickly, like this. So the next one is this over. This is critical. Then the next one is under. That means the damping factor is too small. So the result will be it will reduce very fast. But will do like this, overshoot. Then it will go up back and this, so it will have vibration. In the example of your car trunk, so you pop it, it closes very fast, but there will be a vibration and so on. Later time still try to close. So this is our scheme. All these three solutions are based on the relative value of L, R, and C. Again, we do not try to solve this second order differential equation. We just use this example because we know first order circuit, second order circuit, we're very familiar. We know all these solutions. We know like in first order that solution in this form. In the second order later time, you also need to know the solution looks like this. But for CET, we do not need to know how can you get that solution. You just need to memorize the solution is in that form. So the example used here to show that all these continuous systems can be modeled by first order, second order differential equations. So if you know how to solve differential equations, then everything is very simple. That is the key for this. Does it make sense? Okay. In this 4 years you study, we only deal with the first order, second order circuit. So everything is just like this. Next one, we discuss a basic continuous time systems. First example is you recall the circuit we already learned. So far, when you analyze the circuit, usually it is like a linear circuit, right? Amplifier. So the first one is linear amplifier. That's the first continuous system. So this one can be represented by YT. The output equals something related to the input, XT. So output voltage related to the input voltage, output current related to the input current, or output voltage related to input current, output current related to the input voltage. Voltage current or combination. So with a constant. So that is a linear amplifier. This A is constant, so that means this is linear. The second one is square, right? And we know the diode, right? This thing. And the current related to the voltage by second order polynomials. So that is the square, right? So that means the output equals the input square. The next system is time delay. Time delay means the output is just a delayed version of the input. Right? Your input is totally copied to the output, but with some time delay. All others are the same. So the output equals the input. But I said this is some delay some time. Okay, so delay T0. T sub 0, for example, equals 1 second. That means you have input here, then you just delay 1 second, then the output is exactly equals input, just with 1 second delay. Right? In this case, T sub 0. And if you say T0, for example, equals negative number, that means plus some plus positive. Or that is not a delay, that is like in the future. Right? That's called advance. So like yt equals xt plus 1. That means this output needs to predict the input in the future. This one is called delay. If t sub 0 equals 0, that means no delay, then this is called all pass filter. So everything passes. So yt equals xt. What is this? Yt equals xt. Just a straight line, right? You have a straight line here, then yt equals xt. No delay. Right. The next one is differentiate. That means the output is the differentiation of the input. So, because dx dt. What kind of circuit gives us a differentiation?
First one.
There's an operational amplifier, right? We know this? Open amps, right? There's a like a the circuit looks like this, plus minus, and we have some here, okay, like something here. Is this correct way to do this? This is then the output equals the differentiation of the input, right? Is this C here or C here? I forget. I am at the, you can easily check this one. So this is the differentiator. The next one is what's the next one? Integrator, right? Right? Integrator. That means the output equals the integration of the input. How to implement this? We just switch the position of this R and C, right? So C is here, R is here. So we just switch the position, then this one is the integrator. You already taken math 169. Sorry, 168 integration. This way, look at here. this t means time, means this t is the same as this t. How about this t and this t? What are these two? Are they the same as this one? No, they are not. What is this t? This t is just the integration variable, right? And we can replace this. So this t are the same. This is the variable in the function. This is the integration variable. So this integration is with respect to this t. And this t is the time. This t is not necessarily time. Right? So try to avoid the confusion. Usually we do not write like this. If you write like this, fine, but you need to understand these two t are the same, totally different than this one. They are not the same thing. This one is time. This one is the same as this one. These two are the same, but not same as this one. So try to avoid the confusion. Usually we do not use t. Instead we use tau. Does this make sense? You? For example, I do the integration. So t squared dt, right? From 0 to t. Do this integration. What is this? This one we know t squared integration equals 1/3 of t cubed, right? Okay, then you 0 and t. Now we replace this t with this t. Are these t the same? No. This t is the time, this t is the variable. Right? So now let's do another one. From 0 to t, x squared dx. Right? Suppose this one equals 1/3 t. What do we have here? The same thing, right? So 1/3 x. This one?
No. It's 1/3.
1/3 of
1/3 t.
Of t, right? So this is still 1/3 of t. So now if you say this is x, so that is the confusion. Well, this is still the same. Look at this. This one here, we do the integration. This is 1/3 of x cubed, right? And from 0 to t. You need to replace this x with t here, so that gives us 1/3 t cubed. And we replace this x with 0, which gives us 0 minus 0 to forget it. So this one is better. We understand this perfect, but this one is confusing. This t are the same, but totally different than this t. So that's why we don't like this method. We write x, that's fine, but usually we're just writing in the tau. So we set this one tau here, and this is tau here. So this is tau squared d tau, and this tau. Looks like t, but it's not t. Make sense? Okay. So that's why the integrator circuit system gives us yt equals integration from all the time, negative infinity to the current time, present time t, and x tau d tau. These 5 are typical continuous systems. Do you have any other examples, continuous systems? So far, you learned. We learned this one, right? We discussed this a lot in circuit analysis. This one is just the special. And this is not a linear circuit. This is not linear. Linear means we have only a constant times the input. This one is the input squared. So this is, if you draw this, this is like this. This is not linear. And this one is. And this one is delay. When you design a circuit, for example, communication system, no matter what, this one here, you have input here, and the signal passes through all this black box. You always have some delay, right? The signal transmitted through the media needs time. Even at the speed of light, still need time. So you have distance here, then this one must be delayed. So when you design a system, you may want this delay to be very, very small. Sometimes you want this delay to be very, very large. Depends on what you want. So the delay is not necessarily a bad thing. but most probably it's a bad thing. But sometimes it's good. So this is a time delay. So input, output equals the input. We do not change anything here, except the time is delayed by t sub 0. And the next one is the differentiator. We already know how to implement this with the operational amplifier. We just erase the circuit. And the input related to the output by the differentiation. When you design this kind of circuit, do you have any special requirement? Anything you need to take care of? For example, if this one is a differentiator, so when you design differentiation, so what kind of what thing you need to be aware of? Be careful. Okay, now look at this one. Recall in the first class, if your signal is input, what is this? UT, right? Unit step. Suppose this one is your input. You pass this one through your differentiator. What is the output?
Unit rate.
Right. It's like this, right? Impulse. Differentiation of this equals the impulse. What's the amplitude? Equals infinity. So if your signal like this, then you may have an infinite output, which may damage your circuit. Okay. What kind of input is this? It's UT. So the key here, you have a jump. That means your input is not continuous. Like this. From 0, suddenly goes to 1 within no time. And if you pass this signal through your differentiator, your output will be equal to infinity. It's very, very loud, so may destroy your system. So this one must be careful. When you try to apply this one, usually you need to use something like this, okay? To modify your input signal to avoid this infinite output. This one. Any other systems you already know? We already discussed in circuit analysis. The input is related to the output by some function. Logarithmic. The output equals the log of the input. Have we discussed circuit like that? We also use operational amplifiers here. Maybe on here, what do we have? Maybe like this, right? Yes? You remember this circuit? Or we switch the position of this two, we get what's the anti-log? Inverse log, exponential, right? So if you switch this position R, make this one here, then this is the exponential. So y equals a log input x, y equals exponential. All these systems are continuous systems. Okay? So okay, we discussed the typical continuous systems. The next topic is we are going to discuss the properties of a continuous system. The property. Continuous time system properties. The first property is memory. Memory means you can remember something. The memoryless system the memoryless system means the output at t at some time depends only on input at t. The output at t, at time t, depends only on the input at times t. Does not depend on the input at the previous time or in the future time. So that means we do not need to memorize anything. Any questions on this? All right, now look at these examples. Linear amplifier. The output equals the input multiplied by constant. Is this system memoryless? If it is memoryless, it means the output at time t depends only on the input at times t. We don't need any input at past time or in the future time. Yes or no? Yes, right? Okay, good. So look, t only equals to t. Then just multiply by constant. So this system is memoryless. Any question on this? Okay, now this one. Square. Is this memoryless? Yes or no? Yeah. Yes, right? So again, the output at t only depends on the input at t, just square. We don't need any input at the previous time or in the future. Okay, this one, time delay. Okay, we make a sample. Suppose this one equals t0 equals 1. Eh? So yt equals xt minus 1. Is this memoryless? No, right. Eh? So this one need memory. Why? For example, when t equals 10 seconds, we need the input at 9 seconds, right? 10 minus 1 equals 9. So how can you get this input at 9 seconds? You need to memorize. So we need to know the input at the time other than present time. So this we need memory. If you want to implement this system with a computer, you need to provide a memory to memorize this value. Otherwise, input coming, then it's gone. So you need to memorize this. Does it make sense? Okay, how about this one? The t sub 0 equals negative 1. That means this is t plus 1. Is this memoryless? Still not memoryless. That means it has memory. That means you need to memorize the input in future time. Is this possible? You have a system. Your output depends on the input in future time, and you need to memorize that. You need that. Is this possible? No, right? Okay. In real life, no, wait. But if you want to use a computer to process something, it's possible. For example, if you want to process the stock market data, today you can use, for example, today is Monday, right? Okay, you can process the last week, Monday, then you know the future value Tuesday. So when the time is last Monday, but you already know the value last Tuesday. So you know that's future. But that is not practical. Right? So, but you still need to memorize. So this is has memory, not memoryless. That make sense? Okay, now this one, differentiation. A differentiator, is this system memoryless? Yes or no? Yes? Why you say yes? Can you explain? You cannot, right? Okay, but I know how you explain this. Okay, when you calculate, suppose this is the function fx. I know when you calculate the differentiation, you take this point, you take this point. Okay, this x plus delta x. Okay, so this one is fx plus delta x. This one is fx. Then you subtract, you get this value, then divide by this value. Then you make this delta x approach to 0. That is how you calculate the differentiation, right? You learned this from Math 167. Now you're good. You have good memory. You memorize this one. You say, yeah, I need this value. I need this value. So I need them. This will give us the differentiation at this time. Okay? The differentiation at this time, I need to use these two values. So you need to memorize. Is this your explanation? No? Yeah? Okay, keep in mind here. What you calculate this one? So fx plus delta x minus fx divided by x plus delta x minus x. This one is not differentiation. What is this? This is just the slope from here to here. This is this one. That's not differentiation. Right? The differentiation is we need this one delta x approaches 0. That is the differentiation. When this approaches 0, this one is a single point. So you don't need the value at here, the value at here. You only need the value at this point. So differentiation is a memory list. Does this make sense? No?
So it doesn't require memory.
We do not need memory. And because differentiation is only the property at this point. We do not need the information here or here. We only need the information at this point. In math, we use this idea to introduce the concept of differentiation. But keep in mind, we need to take the limit. So once the limit, this limit goes to 0, that is the 1 point. Does it make sense? Yes or no? So differentiator is memoryless. Okay. Integrator. Does this have memory? No, no memory. The output at t equal to 0 must be equal to the value here. So look at this. Do we need the values only at t? We also need the input value at t before t, right? Does it make sense or not? So we need to memorize all the input values so we can do the integration. So this one is not memoryless. This one needs memory. So look at here. T minus 1, minus 2, minus 3, negative infinity, all these values have contribution to the output. So we need to know all that. Okay, any questions? How to determine if a system is memoryless? You just look at this one here. If it's only t, then it's memoryless. If you need t values other than t only, that's for example t plus 1, t minus 1, or any value before t or after t, then is not memoryless. Here, memoryless, memoryless. This one, look, that is not a T, except T 0 equals 0. That is a special case. Other than T 0 equals 0, this one has memory. And this one, there's only T here. So that has no memory. And this one needs a lot of values. So this one need memory. Questions on this? Alright, that is the simplest property, right? The easiest to understand property of this one. Right? So, do you feel good or not? Okay, next one is a causal system. Causal system means the output at T depends only on input at T or before T. So the output depends on the input that already occurred or is occurring at this time. You cannot depend on the value that in the future. So that is called the causal system. Output at this time depends on the input. The input can only be at this time or already passed the previous time. You cannot say, okay, the output depends on your future input. That is not possible. You cannot do that. That system is not practical. You cannot implement a system in real life with that you need a future input. Does it make sense? Any questions on this? Okay, now look at these systems. The first one, linear amplifier, is this causal? Yes? Yes, depends on the input only at this time. Square. Yes? Yes, also depends on only time. So here is the trick. If a system is memoryless, it must be causal. Because it only depends on the input at this time. So that is causal. This one, delay. Is this causal? Yes. Anyone says no? Yt equals x t plus 1. When t equals 10, okay? You want to know the output when t equals 10. You need to know the input when t equals 11. Right? So that is not causal, right? Okay, so causal or not depends on the value of t sub naught. If t sub naught is 0 or positive, that is causal. If t sub 0 is negative, that means this is plus 1. Then that is not causal, because you need the input in the future time. You cannot do that. This one, differentiator. Is this causal? Yeah, we just said this is a memoryless. So memoryless system must be causal. Is the integrator causal system?
Yes.
Yes, we only need the value at this time and all the previous time, right? Make sense? Okay, now let's make a change. +1. This is still integrator, right?
Still causal.
Is this causal?
Yeah, because you
T
don't-
+1. Do you need the input value at when tau equals T +1, which means compared to this T, is in the future. So it's not causal, right? So if this one is T, okay, that is causal. If it's T +1, T +100, no. Or if it's T -1, yes, that's good. So can only be up to present time. Cannot be in the future time. Make sense? It's good? Now let me trick you again. I put this tau, okay? I make this one tau +1. And keep this T here. Okay? This is the tau here. Like this. Is this causal?
Yes.
Yes, right? Because this one just what's this? This is not time. This is just the integration variable. Who cares? This is not time at all. So you do this integration, you get something, then you replace this one with t. So that is a time. Okay. Causal system. Next one, stable. Stability. A stable system. Just use it. So what is a stable system? The stable system said if your input is bounded less than a constant A, cannot be infinity, right? No matter how large, this must be smaller than some number. 1 million, that's fine. 1 billion, that's okay. But you cannot go to infinity. You must be smaller than some constant. So if you give me input satisfy this condition, if my output also less than a constant B, this B may be different than this, that's fine. It's still constant. If this one is satisfied, this system is a stable system. Can anyone repeat what I said? Anyone? What is a stable system?
If the input is less than the constant, then it's stable on the input side. If the output is less than the constant, it's stable.
Right. Okay. So suppose I give you a system here. Okay? If your input is bounded less than constant, if your output is also bounded, can be very large, but it's bounded, then this system is a stable system. All right, let's look at this. Is this system stable? Linear amplifier. We analyze a lot. We even built some linear amplifier. Is this stable? And you look compared to that definition. If you give me a bounded input, is my output bounded or not? I says no. I heard yes, no. Yes or no? If this one is bounded, is the output also bounded? For example, this one, the input is less than 1 million. Your output will be less than 1 million times A, right? So this is also bounded. If your A equals 1,000, then if this one less than 1 million, then this one will be less than 1 billion. Or 1 billion is very big compared to 1 million, but who cares? It is also bounded. That is the key. It's less than some number. Does it make sense? So this one, yes, is a stable system. How about this squared? Is this stable system? No. No. Anyone says yes? Okay, now let's try. You give me input. What is the biggest input? You just make assumption. How large is your input? The maximum. 100. Okay? Then can we claim your output is less than 100 times 100, which is 10,000? Can your output is larger than 10,000? No. So it is bounded. Your signal input is bounded by 100, then your output will be bounded by 100 times 100. So that is also constant. Make sense? So this one, yes, it is a stable system. Okay, time delay. Is this a stable system?
Yes.
Yes, definitely, right? You give me a bounded X, so I just delay some time. Just move this one on the time axis. I don't even change the amplitude. So if your amplitude is bounded, then the output is also bounded. So this one, yes. Okay, differentiator. Is this a stable system?
You said it's stable?
Is this, I'm asking, is this stable or not?
Yeah, it's stable.
Yes, it is stable. Anyone says no? Differentiator. Recall our example here. Suppose your input is UT. Is this bounded? Is UT bounded? What is the maximum value of UT? Huh? No, I mean, what is the maximum value of UT? How to draw UT? Right? What is the maximum value of UT? 1. Yes? So that is 1, that's the maximum. So is this bounded? So this one is always less than or equal to 1. So definitely this is bounded. This value cannot be more than 1. Make sense? So the input A is bounded. Okay, now let's see. If you input this unit step to the input differentiator, what do you have? What is Y? You take the differentiation. What do we have? Huh? What's the differentiation of UT? Impulse. How to draw impulse? Like this. Is this bounded? No, this one goes to infinity. So now go back to the question. Is differentiator a stable system? No, it's not. Because you have bounded input, you can have an unbounded output. So that is not. How about integrator? I'll give you a simple one. Y equals 1 dt from 0 to t. That's very simple, right? It's just one unit step. This is unit step, right? ut. For better, we say u tau d tau. What is this? Ut differentiation integration is what? Hello, you need to review the lecture notes. The ut differentiation give us an impulse. The integration give us a unit rep. So it equals RT. How to draw RT? Right? So the RT is RT bounded. No. It is increased with time. Right? This one equals T. You said bounded at 1 million. How about when T equals 1 million and 1? Okay, that's value equals 1 million and 1. So how about you said bounded at 1 billion? Okay, the T equals 1 billion and 1. Okay, it's more than 1. So this is not bounded at all. So integrator is not stable. You can just keep this accumulating the result, then your output can go to as large as you want. Questions on this? Let's think about other systems. Logarithmic amplifier. The output equals the log of the input. Is that a stable system? You give it a bounded input. If the output is also bounded, it is stable. That is the definition. Now you think. This is a logarithmic. That means y equals log x. Is there any bounded input that makes the output equals infinity? Any yes or no? Y equals log x. No matter base 2, base 10, base year, okay, that's not big deal. YT activate. Is this a stable system? All right, let me give you a hint. What is an oscillator? What is an oscillator? You have the crystal, the old crystal watch, right? Okay, there's inside there's a crystal oscillator. What is a crystal oscillator? I ask you to go to the lab to make an oscillator. How are you going to do that?
You use capacitors, the transistors.
Capacitors, transistors. Okay, so basically what is an oscillator?
makes the signal go up and down.
Okay, make the signals oscillating, right? Okay, let me ask you a question. What is the input to your oscillator?
Some sort of signal.
Hmm?
Some sort of signal.
Source signal?
Yeah.
What source signal?
I don't know.
In your watch, crystal, this watch, what signal do you have?
Lithium battery.
The battery, okay. The battery is DC, only supplies the power, so you can have an amplitude of the oscillation. That one is not the input signal. We call this amplifier, operational amplifier. That battery is applied at this point, right? This battery is here, VCC. Where is the input? The input is here, right? The battery is not the input. This is the input. And this one is the output. You get, sinusoidal function. Like this. What is your input? Right? Suppose this is a ground. This is a plus, this is minus. Anyone remember that? What is your signal here? VIN. Give you a hint. Do you need input? Yeah? No, you don't need input. The input equals 0. We still get the oscillator. For the oscillator, we don't need any input. The gain equals infinity. So we have output, the input equals 0. So that's give us infinity gain. One type of oscillator is made by logarithmic amplifier. When the input equals 0, this is bounded, right? The input equals 0. Is bounded? Yes. What is the output? Log 0 equals what? Log 0 equals 0. Equals 1. Any other options? Log 0 equals what? 0? 1? Okay, equals infinity. Or basically it's negative infinity. But who cares? We only care about the amplitude. So amplitude still equals infinity. Log 0 equals absolute value equals infinity. See? We don't need to have any input. We have an infinite output. Is this system stable? No. Your input is bounded, it's 0. Your output is equals infinity. Oh, somebody has an objection. Anyone has an objection? I said the output equals infinity. This one is not equals infinity. It has a value, right? This output is not equals infinity. Because infinity, that means your watch is gone, it's damaged. Cannot be infinity. So what I said here is wrong, right? So input is bounded, output is also bounded by some value. Yes or no? I try to confuse you, right? So sometimes it's stable, sometimes it's not stable. So now tell me, is it stable or not? Yeah, the output is large, but it's bounded, right? Your watch cannot go to infinity. That is for sure, right? If your watch can give you infinite output, then you don't need to buy anything. This is infinite energy. There's no way. Right? So this is bounded. But this bounded is not by this. It's bounded by the your device, for example, the nonlinear device. So this one is bounded, but it's not by this logarithmic amplifier. This one still equals infinity. You just, when you do the input, you just cannot input that are infinity. You need to limit it because of, for example, transistor or anything else. But anyway, for this logarithmic amplifier, it is infinity. So now tell me, is it stable or unstable? Unstable. So this one is unstable. Right? This gives you another trick. When you apply the logarithmic amplifier, you cannot ground your input. If you ground your input, your amplifier is not here anymore. Right? Where it is? Trash can. Right? See, look, if you have input here, you ground this ground, right? Most probably that the output will goes to very, very large. Maybe not infinity, but it's very large, may damage something. So do not ground your input of your logarithm amplifier. So it's very dangerous. If you work for somebody, be careful. Right? If you touch it, we are grounded, right? So if you touch the input, it's gone. All right. Any questions? Memoryless, causal, stable, still very easy to understand. Right? Now we are going to discuss some other properties. The first one is called the linear area. Linear. Linear system. We deal with a lot of linear systems. When we analyze a circuit, we say there's a linear circuit. Right? Everything so far, I think we are, even transistors. I mentioned transistor is not a linear device, but we still approximate with a linear circuit with the condition that small signal approximation. That means the input to your input or output to your transistor is small, right? So the output is exponential. It is like this. See, look, it's not linear. But when you said the signal is small, at this point, see, I just approximate this part, it is linear. But don't make the signal too large. Too large is non-linear anymore. Make sense? Right? So what exactly a linear system? We have a lot of explanations. For example, linear system cannot give you new frequency. Right? If you have a system here, it's linear. Then if you have a cosine omega t, that is the frequency, then your output can only be cosine omega t with some maybe amplitude or even a phase shift here. Right? But the frequency cannot change. You cannot have any new frequencies. That is the one property of a linear system. But that's not the definition. So what is the definition of a linear system? We have two requirements. Two conditions must be satisfied for a system to be linear. The first one, assume we have x1 t, that's the input. Then we have yt, this is the output. You have a box. You have input, okay, you get the output. That is just the assumption. No matter you calculate this or you measure this, we don't care. You have input x1, you get output y1. It's good? All right. Now you try another. You have input x2, similarly you have output y2. Now here is the interesting part. If you make a new input which is x1 plus x2, And you are going to have another output, right? And this one is the new output, xt equals x1 plus x2. You add up these signals together. You input this sum to the system. You still get another input, another output. If this output equals y1 plus y2, if this one satisfies, this is called additivity, right? So this is called additivity. If you have x1, you get y1. If you have x2, you get a y2. No big deal. Let's just input the system. Now, you add these two inputs together. If your output also equals the sum of your output, then this satisfies additivity requirement. This one is a little bit not easy to understand. Right? Let me give you an example. This one. Y equals A times X. Y equals A times X. My question is this system satisfy this additivity requirement? Right? Let's see. If you have x1, then you are going to have y1, which equals A times x1. Right? Yes? Right. If you have x2, then you are going to have y2, which equals A times x2. Alright, that's nothing. We just follow these rules. Alright, steps. Now the trick is, if you have a new input, which you add these two together, right? Now we have y, new y. This new y will be equal to, see, y corresponding to x. So that will be equal to ax, right? Good? Yes or no? Yes. Okay. So x equals what? Equals x1 plus x2, right? Okay. So that is A x1 plus x2. And what is this? This one is distributive. So that's x1 plus A x2. Right? And what is this? Oh, this one is y1. What is this? Oh, this one is y2. So this one equals y1 plus y2. That means this system is satisfying additivity. Questions on that? Are you good? Alright, now let's look at this one. Square. Does this satisfy additivity? You just try this, follow these steps to see if this condition satisfies or not. If this one satisfies or not. If this one is good. Okay, we are going to stop here and we will continue next time. Okay? So keep in mind, we are going to get harder and harder. So put some time, more effort, review the lecture notes, and it's better preview what we are going to discuss next time. Okay, thanks.